Super. So, guys, a little bit of just ground rules before we jump into it. For the next 2-3 minutes, chat is open, and you're welcome to continue our weird fun facts conversation there. And as Sukanya starts to chat, as Sukanya starts to share her, the work that she's done for this masterclass with us, we'll close down the chat. Hey, okay, no spamming, okay? Whoever is chipmunk, stop spreading the chat. Okay, I think we're going to pause the chat for now. Okay, guys, you can chat with me if you'd like anything related to the topic. Otherwise, we're going to go ahead and get started. So, for folks who are new, Gifted World is this really fun space where we have weird conversations about different things, and we build community with other people who really love learning. So, I'm going to share with you our website in case you haven't seen it. Everyone would have registered for today's session here on our website. And if you look at this space called events, you'll see all the upcoming masterclasses. Siddharth is going to lead one on math that breaks the internet soon. I'm leading one on how to take photos from being meh to mind blowing. And you'll have a whole bunch of interactive workshops that we do. And I'm excited to see you in either of these masterclasses or courses coming up, right? Sukanya is going to lead one, and we'll talk to you a little bit about it as well after this. And let's jump into it. So Sukanya is a fascinating person. She's a scientist, she's an educator, she's a writer, an award-winning writer. And not just in English, but also in Bengali. And that's really fascinating for me because I feel like I don't know enough of another language to write decently in. And it's amazing for me to meet people who are able to write about science in multiple languages. And Sukanya has led masterclasses and courses for us online for the last year and for many years in our summer program. So more about that soon, and I will hand it over to Sukanya to lead us into the session.
Okay. So good evening, everybody. Welcome to this masterclass. So as you know, the topic that I'm going to talk about is why is gravity so special? So let's look at it a little bit. And I'm going to start by sharing the screen. The only bad part about it is that once if I put in the slideshow mode, I don't get to see your faces anymore. So I don't know whether I'm talking to myself or with or to real people out there. Okay, so here we go. And I'll just Kristen. Okay, enable content. This is I don't. Yeah, that's the problem. Okay. All right, I'm going to start with that. All right, here we go. So there's still people coming in, is it? So, so what I'm going to do is start out by watching a video, which probably many of you have seen. And I have also seen it like at least 100 times because I love it so much. And later on, we'll develop like what the class has to do with this video. And let's see if I can get it to work. So this is a video by the commentator is Brian Cox, and what's going to happen is that they're going to get a vacuum chamber and they're going to drop a feather and a bowling ball together, and it needs a little special setup. And I think you all in your mind you know why, but we're going to listen to him and see what happens. I find it fascinating every time I watch it, and as I said, like I've watched it 100 times. So here we go.
This is NASA's Space Power Facility near Cleveland, Ohio.
Yes, all good.
And it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space. And it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. Galileo's experiment was simple. He took a heavy object and a light one, and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
Okay, so let me see if I go. All right. So I think best thing is, so I'm going to share back again. So could everybody see it properly? All
Yes,
right.
we saw it clearly.
So, so the thing is that we saw that the ball and the feather fell exactly at the same time, right? Exactly hit the whatever platform below exactly at the same time. Do you think if you do it at home, it would work? Does anybody think that it's going to be you can conduct this experiment at home?
I've opened up the chat for you to respond
just for
to
the
everybody.
okay. So everybody agreed that you can't do it, and it was necessary to remove the air, right? And removing the air was a very, very big deal. And removing the air like that to this scale could not have been done without this incredible technology. So you need the vacuum setup, and it was not a trivial vacuum setup. In fact, if anybody went in there, he would die instantly. So everything had to be remote control. Okay, so there's air and gravity in the house. Yes, gravity is everywhere. Okay, so now I'm going to go back to sharing, and so we watched the video, and we'll go back to a little bit of the history of this same idea of why are they falling together, and what did people think about it previously. I mean, did you know right away that they're going to fall at the same time? And And every time you conduct an experiment, there was no high vacuum out there, right? I mean, this NASA technology is very recent. And the fact that you heard him say that Newton knew it, Einstein knew it, how did they know it without having tested it out where there was no vacuum, high vacuum technology? And that's where a lot of thought experiments and physical reasoning come about. So I'm going to talk a little bit about the history. Okay, so, and it's a fascinating history. So we'll start from, yeah, we've done that. So I'm going to start from this, not this one. Why did it come onto this one? Let's, no, how do I get rid of this? And I'm screen sharing. Wait. So this is the slide I need to start out. Current slide? Yeah, here we go. Okay. So here was this gentleman, Aristotle. Most of you have heard about him. He's a Greek philosopher and a scientist who lived this. So we are going back in history like 2000 years ago. And science was done. So Aristotle was a thinker who dominated the thoughts of the world. Like he was like the big boss then. And he was indeed a very, very important thinker. And what he felt, his mode of doing science or approaching questions was that to reason everything out, to do everything by, he thought like you could reach conclusions by pure reasoning. So like one of the things he thought was all the sun and the moon and all celestial objects were perfect spheres, because spheres were the nicest geometric or regular symmetric geometric objects. And he didn't feel that you need to go out and verify that. Similarly, there's a story, I don't know how far it is true, that Aristotle believed that women had fewer teeth than men. And it shows you something, that the mode of thinking was that you don't have to, all you have to do is, so the joke goes that why didn't Mr. Aristotle ask Mrs. Aristotle to just open her mouth? So there was no concept of, in his way of thinking, there was no concept of verifying something by experiment, which is now a hallmark of modern science. So you can get only so far. Reasoning is important, but you can only, everything that seems plausible and logical need not be what nature puts out for you. So you have to, so that concept was not there. So this is what Aristotle believed. Aristotle saw, I mean, I must have seen it around that, heavier objects fall faster than lighter objects. A feather falls slower than a heavy ball. So he said that this is a universal truth. Heavier objects, the heavier an object is, the faster it will fall. So that was what he believed. And that was what everybody believed for almost 2000 years. So that's the thing. His belief system was so strong, and it influenced the whole world so strongly that for the longest time, people did not even think along the lines that when you are postulating something or you believe something is true and you have a logical reason for it, you also have to test it out by experiment. Okay? So that's what he thought. And by the time, time progressed, some rebels, thinkers started having doubts whether Aristotle is true, what Aristotle says is true. And they thought that maybe we should try it out. There was so this was a classic experiment, which was done by a gentleman called Simon Stevin in Netherlands. And he was joined with another fellow called, his name was De Groot. And what they said that, okay, he says that heavier objects fall faster, but let's try it out. Maybe it's not true, who knows? So what they did, Steven and De Groot, they designed an experiment. There was a high tower in a town called Delft, and they had a wooden platform 30 feet below, and they dropped identical shaped lead balls, spheres, and one sphere was 10 times heavier than the other. And what they found, lo and behold, contrary to what Aristotle said, that the balls actually hit the ground at the same time. Now, the thing is that this was not a perfect experiment. This was not a perfect experiment because they couldn't measure the time very accurately. The clocks were not so accurate. They also had to rely on the sound of when it is hitting and recording the time right then. So it was not super accurate by today's standards, but it was something. It was something very important. Like it was a So this was 1586. So imagine Aristotle was 200 BC. So it took this long to try and try and see like whether what he was saying is true. Now notice that here they did the experiment. They didn't do high vacuum because there was no way you could get high vacuum. But they used heavy balls, and because it was heavy balls, as opposed to the air resistance was sort of minimized. So the difference was not huge. So then came a very important person in science who I think completely changed the way modern science is done. And he was the real departure from the Aristotelian thinking. And you might know who this is. This is Galileo Galilei, who was an Italian scientist. And he was I think the Dutch experiment was done a little before Galileo's time, slightly before. Somebody has a question? Maharshi, you raised your hand. Do you want to say something?
Yes. So in the Dutch one, was it a vacuum that they both fell at the same time?
It was not a vacuum. It was not a vacuum. It's not possible to have a vacuum. So the vacuum technology came very late. As you see, like this NASA technology is very recent. This video was done. So the question is that science progressed in small steps. So what they realized that, okay, the feather has a lot of air resistance. But what if I take you people must have also seen that if I'm dropping two very heavy balls, they're going to fall approximately, they're not going to experience a whole lot of air resistance. Air resistance is there, but it's sort of minimized. So they're just trying to do better and better. So Galileo made a huge departure from Aristotelian thinking in the sense that he realized that experiments are at the heart of science. Whatever good theory you have, if it is not verified by experiments, that theory cannot stand. And towards that, he was one of the people who first started using a telescope, and he saw the craters on the moon. When he saw craters on the moon, he saw that the moon was not a perfect sphere, like Aristotle said. And then he saw the moons of Jupiter. Aristotle thought that Earth was the only planet that had moons around it. So a lot of these things that Aristotle said, thinking from pure reasoning and plausibility, symmetry, all of that, by experiment, they were sort of shattered. And he had also, science was always written in Latin, which was not a language accessible to the common man. So he started writing science in Italian, in the language of the people. So that spread scientific knowledge among people much more easily. So Galileo, what he did is that he was from Pisa. His hometown was Pisa in Italy, and most of you know about the Leaning Tower of Pisa. So basically, they wanted, just like the Delft Tower, of course, you need a very high place to drop these things from, right? If you drop them, from this height, they're going to fall so fast, you won't be able to tell. So first thing, you need a very high. I'm not very sure, or nobody is very sure whether he actually dropped the balls or it is something that he was a thought experiment. I mean, he was so sure, he tried it in different ways, and he said, so his idea was, this is the old idea, if you drop a lighter ball and a heavier ball from the Leaning Tower of Pisa, this one is going to fall faster, lighter is going to be staying behind. And Galileo said both of them are going to fall exactly together and they're going to hit the ground at the same time. And he did, he tried it out, and apparently he liked the Delft experiment. They were getting more and more convinced that this is true. Okay. So this is 1564 to 1642, again, like long time after. Yeah.
So
Otherwise,
Kenya, if
yeah,
I might suggest something, and everyone else, guys, there's going to be lots of questions, okay? Because we're
yeah,
still
yeah,
in the mysterious portion of the masterclass.
yeah, yeah.
Now, treat the chat as one parking spot for all your questions. Park all your questions there. As you think of a question, type it out in the chat.
Yeah, then we
Spend
can,
some time
uh,
towards the end. I'm
yeah,
asking Sukanya all of the
yeah,
questions.
then we
Yeah.
can do. Otherwise, like we have time constraints. Huh? I would love to answer in between. Then before, so long after Galileo, so Galileo already, this thought was planted in his mind, not only this just by experiment, I'm not writing down the part because there is not enough time, but he also looked at theoretically how to justify this. So he went a long way. Now, long after that, Galileo saw something in between Galileo and your fancy NASA experiment was when August 2nd, 1971, when Apollo 15 went on the moon, landed on the moon. So they decided that, okay, even then the vacuum technology was not so great. So they said, like, but on the moon, there's hardly an atmosphere, so there's barely any air resistance. So as we are up on the moon, might as well try this experiment. Like we're not going to get an opportunity to do this on the Earth. So they had a hammer, which was 1.32 kg, and a feather, which was so the feather, neither Galileo nor the people could have attempted. So it was 0.03 kg, very, very light. And this was a falcon feather. And I think their spacecraft also was called some Falcon. So it was quite kind of symbolic. And so they dropped it here, the hammer.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Beautiful by those days.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay. So here, again, I don't know what, here we go. So again, they verified it. So it looks like Galileo was correct, and this whole idea of Aristotle was wrong. And objects dropping under gravity doesn't seem to be caring about how heavy, what the mass of the object is at all. All masses fall with the same at the same rate under gravity, right? So which is pretty amazing. I'll give you 2 minutes, 3 minutes to either do a thought experiment or try it out. Now, we don't have a vacuum, right? So this is just back home. So, but I claim that you can still do a little, not so badly. So you have an A4 sheet of paper, right? You have an A4 sheet of paper and a book which is roughly A4 sheet size. Huh? So let's see, I do have A4 sheet. And then I have obviously something that is heavier. So now if I drop these two, are they going to fall to the floor at the same time when they're going to be dropped together? Okay, so Janani is dropping it.
Yeah, but okay, my background is blurred. I'm not sure if everyone can see it.
Yeah. Or they can drop their own books. Yeah, I see Avian also dropping book and paper. Yeah.
Yeah.
Okay. Did anybody's fall together?
So
No.
Viraj is suggesting that we put the paper on top of the book and drop it. It will fall at the same time.
Right. So who is suggesting?
Viraj in the chat, he's
Okay,
suggesting
okay,
that if
okay.
we put the paper on top of the book and drop it.
Paper on top of this. So that's very clever. So anything else? Did
So
anybody?
some people say it was nearly the same time. Everybody says the book is marginally faster than the
Yeah,
paper.
yeah. What about
Was
crumpling the paper? Will that help? I mean, you don't have to keep the paper in the same shape. Is crumpling the paper going to help? Do you think that's going to make it fall faster?
So okay. Lots of responses.
Ah,
I think most generally the consensus is book is falling faster if it's
and
open.
then,
People are saying the paper falls faster if it's crumpled
oh, it's faster. Okay. I would say it would
or
catch
at the
it.
same time.
Okay. Just about the
And
same time.
Rayansh says he tried to make it perpendicular to the ground to reduce
Oh,
resistance.
okay. That's also very interesting that you're putting it like that. That's also an option. So I think so I see lots of papers and this dropped. Excellent.
Yeah. The book fell first. 2 seconds later, the
Oh,
uncrumpled paper fell.
right.
And the paper and the book fell together when crumpled. When
Okay.
crumpled, it's nearly the same.
Yeah. So crumpled seems to cut down the air resistance a lot, because it has a lot. Without that, it had a lot of area, so surface area, and that surface area actually affects the air resistance. So when you have it just falling, it's going to fall at different rates. The book is going to fall faster.
Yes.
Now, there was one answer said that you put the paper on top of the book, right? And that, of course, is the simplest way to do it. You don't crumple the paper, you put the paper on top of the book. If they were really falling at different rates, so the book would leave the paper and fall down. But actually, they're falling together. So by putting the book underneath, you're cutting out the air resistance from the paper. So that's a kind of a clever, devious way of getting rid of air resistance. And there at home also, you can see that an A4 sheet of paper and a heavy book are going to fall together. So that's like a very cheap NASA experiment where you don't need perfect vacuum. Okay, so let's start again over again. Yeah, I know there are lots of hands raised, and I wish I could answer all the questions, go slower, but we'll save it for the end. Now here comes a very important scientist whom all of you have heard about, I'm sure. And that's why I have this little animation of the apple tree. And there's this myth about when apple fell from the tree, that's when the law of gravitation came to him. Nobody knows whether that is true. However, in a place where I worked previously, Inter-University Center for Astronomy and Astrophysics in Pune, they have allegedly, they got a branch from the original Newton's apple tree and planted it there and grew it in Pune. But the point is that Newton had a very similar experience uh, to what you people went through. In the sense, COVID years where nobody could go out, all the schools were closed, and you were sort of stuck home. Similar time, Newton was in Cambridge, and there was this great plague raging through Europe, and that was almost a pandemic. So Cambridge was closed, so school was closed. So he went to his aunt's house in Woolsthorpe, which had no classes, no homework, nothing. No, I think he was, so he sat under in this apple orchard and used to just had a solid time for thinking. And that's when he came up with, he had a lot of free time for thinking, and that's where he came up with a lot of his theories, theories about motion, theories about gravitation. And a very important, very fun fact or a curious fact about Newton and Galileo is that if you remember Galileo's, I think I don't remember if I gave his lifespan. Newton was born in the year that Galileo died. So it's as if like, they were just, Galileo was handing over his legacy to Newton. So what Newton said, two things, two very important things. Some of you, depending on which class you are in, you might have heard about it, may not heard about it. So it doesn't really matter. So one thing is that something that people were always curious about is like how things move. That was the earliest, mechanics was the earliest science ever studied. So he said two things. He said like one thing was that a body will remain at rest if a force does not act on it. And that's no big deal. You will feel that that's quite silly to say because everybody knows that if you don't push a stone, it just sits there. But what is like very non-trivial is that says that even you can even make a body move with uniform motion, like constant velocity without any force, without applying any force, and it will move. Moving does not have to do with applying force. So that's, and he also showed that as long as it's moving with uniform velocity. So if it's not moving with uniform velocity, it has to accelerate. So force is connected to acceleration. Force is not connected to velocity. Aristotle thought force was connected to velocity because he thought like the force of gravity is acting on the ball, and the faster it moves, the more it gains velocity. The force, if the force is more, the more it will gain velocity. So he thought that force is connected to velocity, which is not. So this is his equation. Force is equal to mass times acceleration. Don't worry too much about it, though I'm going to use it a little bit. But he also gave a law of, at the same time, his main concern was how to determine the path of planets. This is something that the Greeks had been thinking about for the longest time. And he realized that there is a force called gravity, which is like mythically associated with the apple falling. That's where he allegedly got the idea. But he formulated a law of universal gravitation, and I colored this word universal in, highlighted it because it's very important, because he found a law that was applicable not to only the apple and the earth, but any two objects, you and me, a watermelon and an elephant, any two objects on the earth are acted on by a force which depends. So first of all, if you have two objects of masses M1 and M2, they're attracted to each other. And they're attracted to each other with equal force. Like not just because this is big or smaller, it's not that the force is bigger, smaller. They're attracted to each other with equal force. And this force depends on the product of the two masses. And it is inversely proportional to the square of the distance between them. What that means is that it will grow weaker with this distance. If you take twice the distance, the force will become quarter of the force. If you take thrice the distance, you'll get 1/9 of the force. So it gets weaker with separation. That's all you need to know. Okay. So these are the two things that he found. Combining these two, he discovered that the planets are going around in ellipses. He found out the exact trajectories. He could predict the trajectories of planets. Okay. Now, when we are talking about force, it turns out that the scientists have classified all the possible forces in nature into only 4 forces. Whatever force you see has to fit into one of these 4 categories. And one of them, the top one, is our very familiar force, what we're talking about, which is the gravitational force, and it's the force between any two masses. So it's a, anything that has mass is subject to gravitational force. Then there is electromagnetic force, which is force on charged particles. Later on, it was discovered, like you've also read about it in class, that like charges repel and unlike charges attract. You have electrons and protons, positively charged protons, negatively charged electrons, and opposite charges attract. And so this is the electromagnetic force between the charged particles. Then the two other forces are, I'm just doing it because I want to list it. And one is called the strong force, and that is the force that holds the nucleus together. The nucleus has protons and neutrons inside it, so it's the force that binds the protons and neutrons inside, and it has to be stronger than the electromagnetic force. Why? Because the protons are all positively charged. If the electromagnetic force dominated, then they would be repelled. Yet the nucleus is holding together. So this is a different kind of force, but it's a very short-range force. It doesn't have any, any strength outside the realm of the nucleus. So similarly, there is something called a weak force, and this is causing radioactive decay of nuclei, alpha decay, gamma decay, all of that. Don't worry about all that. So the point is that they've classified all possible forces into these four forces, and our main focus will be the gravitational force as well as the electromagnetic force. We'll talk a little bit about it. Okay. So we won't worry about the strong and weak force. In any case, they are very short-ranged. Okay. So now let's think about like comparing the gravitational force. I just said like about the nuclear force and the electromagnetic force. I said like inside the nucleus, the nuclear force is much stronger. But what about outside the nucleus, where longer range, gravitation and electromagnetic force, how do they compare? And if I do that, okay, now here again, this is something that happens occasionally, that the slideshow gets a little stuck. So I'm going to start over again sharing. And let's see if I can get it to move. Okay. Okay, let me get out of, can't even get out of slideshow mode. Once in a while this happens. So maybe what I do is I'll go back to the non-slideshow mode, and here I will this should. So this one is Newton. Gravitational force here. Now I claimed, and let me try once more, just because it looks nicer, but if it doesn't work, I'm going to just go back to this. So the point is that, interesting thing is that gravity is a weak force or, compared to the electromagnetic force. And how much weaker? It's like mind-bogglingly weaker. So if you take say two electrons of the same charge separated by a fixed distance r, and compare the electrostatic force between them, electric force between them, and the gravitational force between them. The electric force is 10 to the 42 times stronger, in the same sense that if I took this ratio, I would have 4 with 42 zeros following it. It's that much strong. So it's pretty amazing. Gravity is very weak in this sense compared to electromagnetism. Gravity becomes strong when you have large masses. That's why gravity is important. That's why, like when we have, in fact, there's a gravitation, though I'm sitting in Bangalore and you may be sitting in some other city, there is actually a gravitational force between us, like there is, I mean, it doesn't matter the resistance, but it's so weak. It is very, very weak. So that's why I'm not rushing towards you or you're not rushing towards me. Like it's very weak. Okay. Now, a little bit about electromagnetism. So remember, like Newton died sometime 1770. So charged particles were not, I don't think they were discovered by then. And way after that, way after that, in 1785, there was this gentleman called Coulomb who came up with this law of force between charged particles. And if you look at it, and so it says, and charged particles, of course, are different than masses because they can be attractive as well as repulsive forces, depending on what kind of charges. But if you look at the equation and you remember your Newton's law of gravitation, it's very, very similar. It has an r square on the bottom, where you have masses, m1, m2, you have charges. In the form of the equation, there was a constant g, here there is a constant k. Very similar looking equations. So that's why there is this meme where there's this Mr. Bean as Coulomb and Newton by some other guy. And Coulomb is looking at, Newton has his law of g m1 m2 over d square. And Coulomb is like looking at us, sneakily staring at his paper. And he's copying down the law and he's just replaced his m1 m2s by the q1 q2s and made up a law. And of course, this cannot happen because, you know, like Newton and Coulomb, by the time Coulomb made his law, Newton was dead. But that doesn't matter, it's a meme. The point of it is that the structure of the laws are very similar. This one depends on the product of the masses. This one depends on the product of the charges. Both have this distance dependent. The farther away you go, it gets weaker. Everything is similar, except that in the charge case, you have these constants are different, of course, and the magnitude of the constants make a huge difference. But also there are two kinds of charges. There's only one kind of mass which attracts. So that's the difference. So again, I want to point this out that Coulomb's law is K. So I put force E with a subscript E, that's the electric force. So that's K Q1, Q2 over R square. Newton's law, this is m1, m2 over r square, but I've put a tiny g subscript there. And the reason I've put that g subscript there, you won't see this in books. The reason I've put this g subscript there is that I'm calling this almost acts like a gravitational charge. If you look at these two equations, I mean, all you have to do, think of this as m is also a kind of charge, but it's a gravitational charge responsible for gravity. And so the falls are so identical. So I'm calling this mass, which is the regular mass that you have, that appears in Newton's law of gravitation. I call it the gravitational charge. It's by analogy. Now I'm going to talk about, just like 2 minutes, Newton's second law. And Newton's second law, I think people who have not studied it, it might seem a little unfamiliar, but you have force times what I call, here I use an I subscript. And here I call this mass appearing in Newton's second law of motion an inertial mass, because you know that mass has to do with inertia. What inertia means that it doesn't want to move. You need, like, if you have more mass, you need more force to push it. So mass is a measure of inertia. So that, and this one applies to, this has nothing to do with gravity. This has to do with any force. So that's why this mass that appears here is not specific to gravity at all, you know. So if I look at the acceleration of the charge, now in a uniform, if a charge Q in a uniform electric field, and that I'm going to write, an electric field, the force in a uniform electric field on a charge is the charge times the electric field. Okay, so the acceleration is going to be, if you think of this as ma, acceleration is going to be QE divided by, so I'm going to write it as Q by mi times E. And if I look at acceleration in a uniform gravitational field G, then this is going to be mg, that gravitational charge, divided by inertial mass G. Now the thing is that, so the acceleration really depends on the ratio of the inertial mass to the charge. If I think of these, so one is, now it happens, so it depends on the q over m value. So you greater your q over m value is, more is the acceleration. Now it's an amazing fact of nature that the gravitational charge, or this gravitational mass, is exactly equal to the inertial mass. So what happens here? This is the ratio. If these two are equal, if mg equal to mi, then mg over mi will be what? Will be equal to 1, right? So this ratio is equal to 1. So that means that acceleration will always be g. So all bodies move with the same acceleration in the uniform gravitational field. And that's why, I mean, the mass is just cancelling out. And that's why these two, the feather and the ball, were falling together, because they don't even know, the acceleration doesn't know anything about the mass. It's just like dropped out completely. So, and this is, I mean, this is something that you found by observation. I mean, in the sense that this is something that nature has designed. So that's why a bowling ball and feather will hit the ground together. There are different manifestations of this also. If you take not just something falling down, but if you project something, say if you project a bullet, you throw a baseball, a cricket ball, a football, an elephant, watermelon, whatever you want, as long as you're starting from the same position, throwing it out with the same velocity, it does not care about the mass at all. It does not even see the mass for the same reason. It could be a ping pong ball or a watermelon or an elephant. As long as it's not, you don't have to worry about air resistance. It's going to go and hit the ground at the same time, at the same distance, and it's going to take the same trajectory. And that's pretty amazing. I mean, that's pretty mind-boggling. And this is something that you don't sort of anticipate, but this is what physics is telling you. Contrast with the parts of charged particles in, say, a magnetic field. So if you have, say, take a big, huge horseshoe magnet, and you create a magnetic field, and you put a proton and an electron, and you it's a uniform magnetic field. But one will go like this, one will go like that. Whereas if you took like two masses in a gravitational field, they will go exactly the same path. So gravity is indeed special. Parts of charged particles depend on the charge to mass ratio, which will depend on the charge as well as the mass. That mass is dropping out completely for gravity. So that's pretty amazing. Similar thing that happens is that the time period of a pendulum, so these are the old grandfather clocks, sorry, which go back and forth like that. And no matter how heavy you make the bob, you change the material of the bob, irrespective of the mass of the bob, the back and forth time period stays the same. And all of this is a consequence of the gravitational mass being equal to the inertial mass of the equivalence principle. Yeah? The fact that everything is falling with the, so here also it's a little hard to see because it's not directly dropping, but it is exactly the same principle that it's telling you, that it's actually falling with, every bob is falling with the same acceleration g. Now, this is the thing about science. You're not happy with this. You've seen like now a million examples that they're falling with the same velocity. You've even done the NASA experiment, and same acceleration. They're hitting at the same time. But scientists keep trying to refine their experiments, saying that what if, like, okay, they're almost the same to very good accuracy, but what if, if I take the ratio and like the 10th place of decimal, they are different. So they keep doing experiments. So there is this, so you push the limits, and there is this experiment for the microscope mission, which is doing a space test of the equivalence principle. So where it's taking away, it's a better test because there is no air resistance for sure. You can do things much more in control. And what they basically do, put two similar objects of different masses in orbit, around it and find out, the time period differences. And they found that the equivalence principle is true to the unprecedented accuracy with a precision of 10 to the minus 15. So if at all they are falling with different accelerations, they will be falling with different accelerations. The difference will be in the 15th place of, more than 15th place of decimal. So that's pretty mind-boggling.
Hi, Sukanya. So,
Yeah.
just want to give you a little bit of a pulse of the class.
Yeah.
There's a whole bunch of interesting questions from people who got it and have a few more questions. I think we have some kids from the younger grades with us. If we can have a brief overview of what we've covered in the last few slides in a slightly simpler form for them to grasp.
Okay. So basically, what we looked at is that all bodies. We're trying to find a reason why all since the feather and starting with the feather and ball experiment, why these all fall with the same acceleration, and we found a justification for it from what Newton told us about the law of gravity and the law of motion, and there, noticing that this happens, the fact that both objects with different masses will fall at the same rate in a gravitational field is very special to gravity. If you take two different masses, two different charged particles, and make them fall in an electromagnetic field, they will not fall with the same acceleration. They will not stay together. So this is something very special that happens with gravity, and it's called the equivalence principle, because these two fall with the same acceleration. All masses are equivalent in some sense. The gravity doesn't see them as different in terms of falling. Okay. So I think, like, I have just a couple of minutes, right? I just want to show two more slides and a couple of more slides, and that the idea is like now, you've seen astronauts floating around in space, right? The pictures of that. So now we're going to look at two different cases. So here is an astronaut who is like floating in a rocket with the engines turned off way out in space, okay, way out in space. So there is no strong gravitational field. Essentially, it's a zero gravity, far away from other masses. So he's just floating out there, no fear. Now, the thing is that it's exactly the same. The claim is that if you're in an elevator and God forbid the elevator cable cuts and you're just like falling freely under gravity, you will have the same experience as this guy. So to give an example, what will happen if you drop a ball while you're falling in an elevator with this cable cut? What do you think will happen? And we already know what will happen because the ball and you are now falling at the same rate. So you will just see the ball standing still. So you will feel that there is no force on it. So it's not falling. So these two situations are exactly equivalent. And that's why astronauts are floating around. I mean, though they are in a gravitational field, they are in that cut cable kind of situation, and they see objects floating around, and they themselves are floating around. The opposite, so this is like this is the International Space Center, which is the picture here where astronauts are falling around, floating around. And this is a picture of the International Space Center. It goes around in an orbit, high velocity. So you might think like, why is it compared to something falling object? And that's a little confusing. So though it has a horizontal velocity along this orbit, as far as the gravitational attraction of the Earth, it's actually always falling towards the Earth, the same as the apple, the same as the feather. It's just that this other velocity is making it going around in orbit. So that the property of this free fall under gravity is the same for the space station as well. Now, I'm going to talk about the opposite situation, where gravity can be, on the other hand, also simulated by just acceleration. Okay, so when you imagine you're just standing on a platform, right, at home. So why are you not going through the floor, or why are you not floating up? Because gravity of the Earth is acting on you, and the bottom is giving a normal reaction, pushing on you. That's why you feel that. So here, if there was no gravity around, free space, but instead you're simulating gravity by accelerating it upwards exactly at the acceleration, 9.8 meter per second square. And exactly that's what you will feel, that you're pressed towards the ground. Similarly, if you have an elevator that is going up, you must have experienced that when you're just going up, you feel a force on your, as if you're like the ground is pushing you up a little bit. So if an elevator is going up exactly at 9.8 meter per second square, there is no difference between that and a rocket accelerating upwards at 9.8 meter per second square. If you drop a ball, the ball will fall exactly at the same rate. So this is what Einstein's statement of the equivalence principle was, that there is no experiment that can distinguish a uniform acceleration from a uniform gravitational field. They're exactly equivalent. So if you are going in a, there's no way, if just like Brian Cox said, that if you didn't see the background, you wouldn't know whether the ball is standing still and you're standing still, or actually you're falling under gravity. Only because you're seeing the background, you know that you're falling under gravity. In that same experiment of the ball and the feather, if you had a video camera attached to your body and you were recording the ball continuously, what would you see? Would you see the ball falling? No, because you're falling exactly with the ball at the same state, same rate. So you'll just see a still picture of the ball. So looking at that, you wouldn't even know that there's a force acting on you. So that uniform acceleration and the gravitational field are exactly equivalent. And this is what Einstein said. And Einstein also had the feeling that if trajectories under the gravitation in gravity do not depend on the properties of the object, they don't care about the mass, right? All masses are falling or using the same trajectory. So maybe it does not have to do with gravitation is related to. So here I'm just like pushing it to the boundary, and you don't have to worry about it. This is just something that you can study later, that maybe it's related to the properties of space itself. You know, like it's not, if it's not within the body, what is common to all these bodies? They're traveling through the same space. So maybe, you know, like gravity is a property of space-time, traveling through the same time, traveling through the same space. Maybe that's what it is. And that's what later, beyond Einstein's theory, Newton's theory of gravity, later on, the equivalence principle is what was the starting point for gravity. Well, Einstein gave a new theory of gravity, which in the video also they mentioned, that which looked at gravity not as a force, but as resulting from distortion of space-time. So I'll just give you a tiny example. So if there were two ants traveling on a flat sheet and they're going parallel to each other, they stay at the same distance. They feel that there is no force between them. Two ants traveling on a tennis ball, trying to stay as straight as possible, are going to move towards each other because the background is curved. So from an outsider, they might think that they are attracted to each other, but they're attracted to each other, but actually what is happening is that there is no force. It's just the background is curved. Similar with a saddle, and you'll see that they're moving away from each other, but that's not due to a force. It's because of the space itself being curved. So this is what Einstein's new theory was. And I'm not going to get into a detail. This is just a teaser, and that's a story for another day. So I'm going to stop here. And now we are going to, I think, Janani, and they're going to tell a little bit about the course, and then we can take some questions.
Yeah, we have a whole bunch of questions.
Lots of questions, yeah.
I've been fielding a whole bunch of questions. It's exciting. I'm looking forward to the Q&A. So what amazes me, Sukanya, is about as a person who's not a physicist, right? Just a curious person. This idea of space is so amazing and fascinating and beautiful and all of that. And also there's so much of this math, this curious stuff that you can, dive into and explore. I would happily, will admit that half of this masterclass is new and perhaps not yet understandable to me.
Yeah, I think like
Uh,
it's a big spectrum, right?
Yes.
Where there is some mathematics in there which will be accessible to somebody in 8th or 9th, but not to 6th probably. So
Yeah,
yeah.
definitely. And I think the fun of being in this masterclass is it's okay not to know,
Yeah,
it's okay not to
yeah.
understand.
When you learn these, then again it will come back to you.
Yes, it'll come back, definitely. Okay, great. So let me share something, guys. So I want to know before I do that, I want to know how many of you learned something new today. Can you put it in the chat? You can just say yes or no. Learn something new. Yes, amazing. So many yeses. Okay, super. I feel like every time I talk to Sukanya, I learn something new, and I'm so glad that you guys got that chance. So if you enjoyed learning with Sukanya, and if you are curious to learn more and you want to like, challenge yourself and learn more than what school might help you learn, then Sukanya is actually leading a course for us at Gifted World this April. And so if you want to spend a little time learning, we're talking about mastering mechanics and a little bit more about forces and physics and those kinds of things. And this is for grade 6 to 8, but 9th and 10th can also join us if they're interested. Yeah, this is for any board and it will be beyond what you learn in class. So if you're curious to push yourself and learn more and learn in a way that you can ask a lot of questions like what you're doing today, and please feel free to sign up. I will share a link on the chat and we can talk more about this. But this is 5 sessions in April. So April 5th, 6th, 9th, 12th, and 13th. Right, and you'll get a chance to talk in a smaller group with Sukanya, and you'll have a chance to ask a lot of questions to us on email and those kinds of things, right? Super. So I'm going to share that in the chat, and then let's jump into Q&A. Yeah.
Actually, because they are
Sukanya, could you tell us a little bit about the course as well from your point of view?
Yes, please.
Since it's something that you've taught in the past.
Basically, this course is about, I mean, it's not completely disconnected from what you're learning. So, for example, it will be about mechanics and pieces of it you're learning, but I think it will be beyond what, looking at it in a slightly deeper perspective and trying to challenge yourself about questions that you may not have thought about or historical connections and trying out little experiments as well. I told you like how important experiments are and connecting it to the theory, understanding mechanics in a deeper way, like and asking, like if I were in a, I mean, maybe I've learned this law, but how would I see it differently if I was traveling on a spaceship, if I was traveling on a train, would my observations agree with the person who's on the ground? How will they disagree? All these questions within the framework what you've learned in class, but you just have to push your boundaries a little bit. Yeah.
Well, thank you so much.
Yeah. Okay. Yeah, you didn't understand the last slide, and it. I mean, I deliberately, you don't have to, because I just have to pushed it a little beyond to just. This is what I'm saying is that Einstein created a new theory of gravity, which superseded Newton's, because and the guiding principle of Einstein's theory was what we learned today, is the equivalence principle, that everything falls at the same rate. And but the way he formulated it was a highly mathematical theory, but at the heart of it, this is here. And he essentially somehow talked about a very revolutionary idea that gravity really is not a force like all the other forces. It's like a manifestation of your space being curved. So you're seeing things diverge not because they are being pushed apart, but somehow the invisible background that is there is all topsy-turvy, and the trajectories are just following that. But don't worry about it. This is just like, don't worry about the last 2 slides. Just in case it pushes you to learn about it or think about it. The mathematics in it is also very advanced, so don't worry about it really. It's just an idea.
So we're putting out a little bit of a slide, a poll. So Siddharth will be launching a poll. So if you are curious to know more about the course, or if you have something like questions about the dates, those kinds of things, fill this poll and we can chat afterwards. And so that discount of 15% is available for the first 10 seats. So this is a good way to fill the poll, and then we can talk about it later, right? So we'll give you guys a minute, put in your details. You can do that.
Actually, I think like with this crowd, with whatever the initial fun facts they share, an estimation course would be very nice actually.
Definitely, yeah. So,
how many times it goes around the moon and all that we can work out.
So, Kat, you want to talk more about that?
One moment. Yeah, so actually, Sukanya is the one who taught me about estimation problems, and I have since then taught it a few times, but we'll definitely put together a course on it. It's this really
please do, because since they are so curious about, how these, because they're learning these facts, but the question is that how do you get to these numbers? So that's an important question.
Yeah, definitely. So just wanted to also share about course timings. So what we've done with all of our courses, in fact, is that they're all happening on weekends and on weekday evenings, because we realize that with such a broad audience across India and the Middle East, someone or the other is in classes and someone or the other is in exams and someone or the other is in holidays at the same time. So we're just doing it at a convenient time for all of you. So it would be weekend, Saturday, Sunday evening, then on a Wednesday or Thursday evening, and then again Saturday, Sunday evening. So just in 2 weekends, the course is done. You've spent about 8 hours learning from Sukanya in contact sessions, and then another 2-3 hours of homework. So that way it's a rather easy way to get this learning in. And there are many, many more courses that we're offering through the summer that we will walk you through as well. And if you like the large numbers part, in April, about early next month, we're doing a session on maths that breaks the internet, which is how quickly do numbers grow if you just enable a sequence of numbers to keep growing. That's the basic idea, but we're applying it to a situation that's quite common to all of us, which is how quickly do videos become viral.
And just put it in the chat. That's a free session as well, so you can feel free to sign up for that.
Yeah. And so maybe while this is happening, shall we start with the questions?
Definitely.
Yeah.
Okay. So we're going backwards from the bottom, right? Because there's a huge...
Everybody's hand up, yeah.
So Ritvik is asking, is the falling of ISS the gravitational pull of Earth?
Yes, absolutely. The gravitational pull of Earth. Yeah, purely by the gravitation, because it's going in an orbit, and the main force is along the line between the Earth and the ISS. So it's always towards the center. The Earth is at the center. It's going around in an orbit. So it is the gravitational pull of Earth. I mean, there might be other stuff out there, but the main pull is the gravitational pull of Earth. Yes.
Super. So Zen has a question, but I'm not sure if I've understood this correctly. Is air an acceleration of gravity that opposes it? Do you?
Well, I see where he's coming from. So look at it that the air resistance is a force. There are two things: force and acceleration. And force is acceleration is force divided by mass, force per unit mass. So air resistance is a force. Gravity is a force. Air resistance will also have an acceleration associated with it. Yeah, whatever the air resistance force divided by the mass will give you an acceleration. You can have an acceleration due to air resistance, yes. But that will be an opposing air resistance, opposing acceleration, right? Because this is trying to fall, and that's trying to make it not fall. Let's put it that way.
Okay. Bhumika says, I didn't understand the equivalence principle.
So the equivalence principle is what is saying is that it's a little subtle, but at the heart of it, it is that the many ways of looking at it. At the heart of it is that this whatever mass is appearing in your Newton's law of motion, inertial mass, is actually the same mass that appears in the law of gravitation, and these need not have been the same. Because they are the same mass, the equivalence principle is really saying a mathematical statement about why all bodies of the same mass are falling at the same rate, why the acceleration due to gravity is uniform. Because why it does not care about mass. And that's why I wanted to contrast it with charged particles, because charged particles in a uniform electric field do not fall with the same acceleration. Yeah. If you put charges on, if I put different charges on these feathers, let's put it this way: if I put it different charges on these feathers, feather and the ball, and gravity will not care about charge because gravity doesn't, it's not sensitive. But I also added an electric field there. I would mess up this falling together, because the electric field does care about the mass, and because that acceleration depends on the charge to mass ratio. So if that is different for each of them, so one way of seeing it is that if I in gravitational field, this happens only in gravitational fields, pure uniform gravitational fields. It will not happen in any other force field. Yeah.
Okay. As Bhumika, do you feel like that your question is clarified? Yes. Okay, great. So let's actually quickly go to the people who patiently raised their hand in waiting. Virat, did you have a question you wanted to share?
Yes, ma'am. I have two things, one question and one fact. So the first question is that isn't gravity the weakest out of all four forces?
It is. It is. It is.
Although being the most populated force, it's the most less powerful
It's
force.
so weaker. So if you remember the formula, the law of gravity, it was m1 times m2 divided by r squared. So now it will be, and there is a constant sitting in front of it called g, which is the universal gravitational constant. And that's a very tiny number. And that's what makes it weak. So now if you want to fight that weakness of that number, the only way you can make gravity strong is to make the masses huge. And that's why we feel the effects of gravity with Earth and Sun and stars, where we have huge masses. That's where gravity becomes important. That's why that's how it's becoming strong. But if you take the same masses and compare that, like I did for the electrons, so if you take two masses with the same charges and the same masses, the gravitational force will always be weaker than the electric. So here, for example, if the Earth and Sun and everything was charged, gravity will not be able to, the electromagnetic force will overwhelm gravity, because, and it's becoming significant only because the masses are so big. So that's why we are always talking about planets, stars, meteorites, asteroids, huge objects compared to that's where it becomes very strong, sustaining.
Interesting.
But it's weak compared to all the other forces. That is true.
Hmm.
But you have to understand what weak and strong mean. It's always relative to each other, right? Yeah.
Great. Shivdat, you had a question?
Yeah, so, ma'am, like you said, masses of the bodies in space are important, and that's where gravity becomes important. So can you explain all the effects of gravity in situations of things like a black hole or a white hole? A white hole is just a theory, but still, as
I don't even
yeah,
want to talk about black holes and white holes, because black holes involve a lot more about, it involves, actually, it's much beyond Newton's theory of gravity. It's all about Einstein's theory of gravity. But a black hole is a situation where, there is a situation where gravity, as I said, it's connected to mass, right? So if you make the mass large enough, and that's why black holes form, because if you have very, very massive stars, very, very, very massive stars, uh, the gravity starts to dominate in them. And the stars are stable because inside stars you have nuclear reactions going on. So that produces heat. So that produces an outside pressure. And the stars stay stable because the gravity is trying to push it, the self-gravity, the various layers are trying to make it collapse because it's very heavy. And it's holding together because of that nuclear, internal heat pressure. When the nuclear fuel is exhausted, then if it's a very massive star, it starts to collapse under its own gravity. So a black hole is formed when a star actually collapses to completely under its own gravity, and the mass becomes so dense that even light cannot escape. So there are lots of intricacies going into that. I don't want to get into this. Is even Newtonian gravity is not that trivial to understand. So I don't want to get into black holes at all. I know it's everybody's dream to talk about black holes, but it takes a lot of further study to completely understand. That's roughly what is happening, because if gravity becomes very strong, and because very massive stars collapse under their own gravity. Yeah.
Interesting. I am curious if maybe we should have a full conversation about black holes at some point. It does come up with every physics class.
Oh, every physics class. Oh my God, because of all this.
Yeah. Okay. Abhyan, did you have a question?
Ma'am, my question is that a planet, its gravity is usually caused by a planet's core, but then what happens if someone somehow digs a hole straight through that planet, though? Like, will a person just be stuck in the core or something, or will it just go to the
That's an
other
interesting
side?
question. That's a interesting question, and actually, yeah, and that's not that easy to understand, because if what happens is that you sort of, if you're digging a tunnel through the earth, you can work out that what you're going to do is you'll sort of oscillate. In an ideal case, you'll sort of oscillate back and forth about the center, because part of it is going to pull you this way, and part of when you're going to the other side, it's going to be pushing you that way. So, but you'll have to work it out, really. Yeah. So it's not easy to walk through the earth and come out on the other side, because gravity.
Yes, ma'am. Also, it's just really like a hypothetical question, because I'm not sure if anyone can really do it really.
Yeah. It's a theoretical question, of course, but no harm in asking theoretical questions, because, if you're actually, if you're going to the center of the earth, in the realistic earth, it will be too hot, and, you're digging a tunnel through. But if you did dig a tunnel through, what would happen is that you will sort of oscillate back and forth, the center.
Going back to your Thank you, Avian. Going back to your original theory of how Aristotle viewed the world, this is what abstraction and the math of it actually enables, right? These kinds of answering hypothetical questions.
Yeah. Hypothetical questions are still there. I mean, of course, they have a lot of value.
Yes.
In fact, see, all that neither Galileo nor Newton could actually verify the fact that they fall exactly at the same rate, because they could never get rid of the air resistance. So their experiments were not
sorry,
perfect.
Sukanya, suddenly your volume dipped. Is your mic covered?
Oh, really? Are you okay now?
Yeah.
Is it better?
Yeah.
Maybe. So, I mean, they were thinking theoretically, of course, and thought experiments have a large role to play. I mean, And that's, I think, like Gen-wise summer also, I'm doing a course which is called the 2 feet of science, and which is a quote from Robert Millikan, a Nobel laureate, who did a very important experiment of determining the charge of an electron. And he talks that this is really experiment and theory at the 2 feet of science. You cannot walk with 1 foot alone. So they just go sort of together. Yeah.
Okay. So Maharshi, you had your hand up.
Yeah, tell me.
Yes, so ma'am, some person asked that the gravity is weaker than other forces, but ma'am, what about planets such as Jupiter or the Sun? Their gravity is really strong. So
it's very strong. Yeah, very strong.
Does it mean that at those places gravity is stronger than the other forces?
Well, it depends on how you're going to compare. Yeah, forget the other forces. So don't worry about that strong and weak force. But if I just compare, because they don't exist outside the nucleus, their range is very short. But the way to think about it is that gravity is very important there because the masses are very big. Because the gravitational force depends on the mass. And now if you make the masses very big, the gravitational force can become very big. Like that G constant sitting in front is very small. That's what makes it weak. But now if I really were to put charges also on Jupiter, so the thing is that if I compared it to the force, if I were put charges on Jupiter and let's see what else, maybe the sun, it's a hypothetical thing, and there is a gravitational force between them. Now there will be an electrostatic force also between them, right? Because if I put charge there, it's not possible, but say I did. In that case, in that situation, the electrostatic force will be much, that 10 to the 40 times bigger than the gravitational force. So, so it's compared to that, like, but if you look at just the gravitational force in between you and me, and I calculate it, and that's also interesting calculation, that if I put in my mass, your mass, the distance between you and me, and calculate it, it's going to be a very, very small force, very tiny force, because that, if you remember that G constant sitting in front of M1, M2, our masses are also small compared to the sun and the earth. So everything is more or less small. Then the distance is also, like the further we are apart, it will become weaker. But now, say, for example, I compare the force between you and me and Jupiter and Sun, if they were separated by the same distance. And that would be huge. That would be much bigger because the masses, it all depends on, is the product of the masses, right? Because the masses will become big, the force will also become big. So it is weak. So you can do the comparison two ways. One, you can compare it with the electrostatic, or you can compare it with Earth objects versus celestial objects. And then you will know why the apple and the Earth versus Jupiter and the Earth, why that is so much bigger, right? So,
okay. So, ma'am, if we compare it to the electrostatic force, then always, whenever we try it, even if the mass is as big
yeah. If you're working with the same masses, and I put the same charges on Jupiter and this thing, Jupiter and Earth, and now I calculate what is the force between the electrostatic force between it will be more than the gravitational force. So, but fortunately, we are lucky that all these objects are not charged. So we are okay with gravity putting everything in orbits, and we see sunrises, and so that's the. So there are two comparisons. One is the electrostatic versus the gravity. One is the gravity versus gravity, in the sense that why is gravity such an important force in for the skies? Because the masses are so big, and their gravity is the dominant force, right? Their gravity is the dominant force, no doubt.
Okay, thank you.
We have some questions in the chat also from who've been patiently waiting from the beginning of the course.
Sure. Yeah.
We were taught that the more the mass, the more the weight. Here, weight refers to the product of mass and gravity.
Right.
I'm not able to get how two different objects of two different masses are experiencing the same gravity. Can you please explain? I am confused.
No, they are not experiencing the same force. The force, you're absolutely right. So the one with the greater force, greater mass will have more weight. And weight, remember, is a force, right? When they're saying they're experiencing the same gravity, quote unquote, what they mean is that they have the same acceleration. The g is the same for all of them. So no matter what mass you take, the force W divided by M is the same for every mass, right? So that is what is meant by the gravity. So gravity is the same is not the correct statement. It's the acceleration due to gravity is the same. So that is saying that this a massive object and the ball has more weight. Feather has more weight, less weight. The gravitational force on the ball is more than the gravitational force on the feather. No doubt about it. And mg is absolutely correct. What we are talking about is not the force, but the acceleration. Forces are different, but the acceleration is the same. But no matter what mass you take, the acceleration is the same. That's the key thing. So that's what's meant by so g is the same, not the gravitational force, but the gravitational acceleration is same for every object that you drop from on the earth is going to fall at the same rate. So you calculate their weight and divide it by their mass. That ratio is going to be the same for every object. That's the key thing. Yeah.
Interesting. So I'm not able to find it now, but I remember one of the chats was talking about how race car drivers experience a different amount of, something about like if everyone gets on Earth being 1G and race
Okay.
race car drivers experience 5G. There was something like that.
Right. Also, these loops doing, so that is an effective, not only the gravitational force, but it also is something that you have to counteract with staying on the track. If you have a circular track or a vertical circular track, that does not have to do with pure falling under gravity. It's true. It's actually addition of two forces, not only the pure gravitational force, but it's true that they will experience, you can have more than G, but that's not a pure gravitational force really.
Okay.
Yeah. So that will take a little time to explain, but he's right. He's right, but it's not pure gravity. Yeah.
Due to the acceleration. Sure. So I know we have lots of questions, guys. We'll get to everybody, okay? This one last one before we get to the people who have raised hands. I think that if an object was thrown or a bullet was shot in outer space, it would remain in motion until it hits an object. Is it correct?
Remain in motion. Yes. That is correct because in outer space, it's actually, if there is no significant gravity, what will happen is that Newton's first law, right? Something is shot out and it will just travel in a straight line with uniform velocity. It will keep going. It will keep going forever if there's no air resistance. Yes, it will stop if it hits an object. That's true. That's correct.
Okay, super. Okay, so there was a bunch of conversation on whether it will stand still or whether it will be pulled by gravity of other celestial
objects. No. I'm talking about when you're looking at outer space, I'm doing a very idealized thing. That every case is you have to state it clearly. When you're talking about space, Just like I looked at that, showed that picture of the rocket with only stars, far away stars. What I'm talking about is like a lot of empty space where there are no nearby objects exerting gravitational force. So that kind of in space, I meant that if there is no gravitational force, no nearby planets, then if you shoot or objects, then if you shoot it, it will just keep going. Yeah, it'll go with the same velocity. If there is a gravitational, there is an object out there, then that trajectory will depend on the attraction of the gravity. That will change. That will accelerate. That will be attracted towards it, no doubt about it.
Super. So while
So you have to state your question like whether it's very far away from all other celestial objects. So essentially it's an empty space and you've shot it out of a rocket, which is, like with its engines turned off. And it's just like going without any force on it, right?
Right. Interesting. So we have, guys, I'm sure we'll still have a lot of questions. So if you feel like your questions are answered and you have other things to get to, feel free, and we're, glad to have had you. Please leave a comment in the chat about what you experienced in the session, but we'll get to all the questions now. So Shivdat has a follow-up question to his questions on black holes. Shivdat, are you here?
Yeah, so, ma'am, I know that we're not talking about black holes exactly. Ma'am, about the sun itself. Ma'am, we know how if we shoot something which has a nuclear content in it, the sun absorbs it and it grows more huge. And we also know that it maintains the solar system, like the balance and gravity of the solar system. And ma'am, just in case, like, or after when the sun does die up, ma'am, it turns into a black hole, which reverses, I guess, it kind of reverses the gravitation.
Actually, the sun will not turn into a black hole ever. That's just so it is a little more complicated mechanism because there is a limit. Stars, the end state of stars, they have different fates, and depending on their starting mass. So if you have, there is a chance to become a black hole only if you start out collapsing with something that is at least greater than twice the solar mass. So the sun is exactly the solar mass, so it can collapse, but it's not going to turn into a black hole. What it ends up is what is known as a white dwarf. So it ends up in a stable state, but it does not. So to collapse into a black hole, there is, in fact, the very famous physicist Chandrasekhar, he did this calculation actually as a 19-year-old on his way to England on a ship, realizing that for a star to be collapsing and reaching a stable state and not collapsing forever, the star has to be, the star will keep collapsing only if it cannot turn into a white dwarf if it has more than 1.4 solar masses. So, and it turns out that the current understanding is that it has to be at least more than 2 solar masses. Solar masses means the mass of the sun. So by definition, since mass of the sun is only 1 solar mass, so it's below the Chandrasekhar limit, it's below the neutron star limit. So sun is not going to turn into a black hole.
So even if it does turn into a white dwarf, ma'am, I'm pretty sure that the white dwarf has an opposite movement of a black hole. Like it pushes out rather than pulling it
White dwarf
in.
is a very normal star. White dwarf is just a dead star which does not shine. That's all. It's like a pretty boring star, and it just collapses to a very tiny, dense state, and it just stays stable and does not shine because it has no nuclear fuel anymore. But nothing dramatic happens with the white dwarf. A star
Ma'am,
dies as a white dwarf, or it can
ma'am,
turn into a neutron star, which is slightly more higher. Yeah.
ma'am, so sun being something that radiates light and heat, not radiates, but gives out light and heat. which being forms of energy, does this mean that gravity can also violate conservation of energy?
No, it does not violate conservation of energy in the conventional sense, because the thing is that it's creating energy, it's radiating away, and that energy is accounted for. So it's just when something is losing energy, heat, and it's radiating, you're creating energy, nuclear fusion. That's what's happening in stars. That's creating energy, and that's given off as heat. So that's all accounted for. The heat that is radiated away is the part that is created in the nuclear fusion. That's all. No violation of conservation of energy.
I definitely feel like we need another astrophysics conversation for everybody.
Yeah, there's a lot of astrophysics going. I didn't mean to get so much into astrophysics as such.
No, definitely. I feel like there's a lot of curiosity around it.
Yeah, there's always curiosity about astrophysics. Yeah.
Okay, I'm going to ask Zikra to unmute and share her question.
Hi, I just had a doubt. Gravity, basically, pulls you towards the ground. So, this is if the world was flat and gravity was still there, how it work?
Yeah, I guess still it will pull it towards the ground. Yeah, yeah. So there's not that much. The world is not flat. That is true. So the law of gravity, I guess, even if it's so let's forget about the Earth. So on your say you're falling off. I mean, not. I mean, this is a hypothetical situation. Say you're falling off the roof. Not you, but somebody. Is someone falling off the roof to the ground, and near that ground, the Earth is approximately flat. Earth becomes, you see the curvature of the Earth where you go to very large scales. So locally, Earth is still flat and gravity is perfectly there. So there is no harm in, you can even create a flat-shaped object. And see, gravity will act, I mean, there's nothing special about the Earth. And that is something that's very important about Newton's universal law of gravitation. Any two objects that have mass will have a gravitational force with it. And it can be a flat sheet of paper and a coffee cup. They have a gravitational force. So the shape as such doesn't have much to do with it. The mass has to do with it. For magnitude of the gravitational force will depend on the product of the mass of this cup and the A4 sheet. Yeah.
Still have
so even if the Earth were flat, there would be a gravitational force. Yeah. On it. Yeah.
That is a very interesting.
And it's a very good question. It's a very interesting question. Yeah, it's a very good, interesting question. And now, why the planets are round and all that? That's also a very is a combination of gravity and rotation and various things. As a matter of fact, this. My daughter teaches in a kindergarten school, 5 and 6 year olds, and there they were asking them, in this planet week, why are the planets round? Why do you think the planets are round? So one of the children said that if they were pointy, they would hurt the astronauts' feet. So that's why they're round. The moon is.
So Kanya will, I think Saurabh also has been waiting. Saurabh and Viraj have been waiting for a long time.
Yeah.
Wander back here. Saurabh, did you have a question to ask?
Yeah.
Ma'am, now gravity is always pulling us towards the earth. So how do you escape gravity? How do astronauts go out of the earth's sphere of influence or just live?
That's a very good question. Very good question. That it turns out that you have to, it turns out that there is something called an escape velocity, right? And you can work out that if you, it's just like, what happens that that when you throw a stone, right? You throw a stone upwards, every time it comes back, right? And it turns out like you throw it harder, it takes longer time to come back, right? Now it turns out the Earth's gravitational field, if you work things out using Newton's laws and gravitational, there is a, if you throw it hard enough, it's never going to come back. And that hard enough velocity is 11 kilometers per second. If you were able to throw, and that's called an escape velocity. So if you actually manage to throw a stone or whatever, your spaceship or whatever, that you push it out with sufficient velocity, it turns out that it'll keep going forever. It's not going to come back to Earth. So it's never going to accelerate to a point that it goes zero velocity and comes back. And this is something you can calculate and show. So it is possible. It is possible. So then, a lot of things happen because in our daily life, we don't see it, right? Because you're right, like it's always attractive. So every time we throw a ball, nobody has ever seen that somebody throws a cricket, no matter if you throw, this Virat Kohli or whoever is going to throw a ball with it can cross a boundary, but nobody have ever seen a cricket ball go out and never come back again. Yeah. So it is kind of hard to believe, but it is possible. And one can even give the exact velocity that you need, like 11 kilometers per second, which is actually very big. If you can throw something with more than that, it will escape the Earth's gravitational field.
Yes, and ma'am,
it will still be pulled back. It doesn't mean that it's not going to be pulled back. So it's a subtle question, actually. It's a very good question because Earth is always pulling it. But its pull is never strong enough. If you're throwing it that high, that hard, it's constantly slowing down because of its pulling. But it will never be able to pull hard enough to bring it back. Let's put it this way. Yeah.
and ma'am, how do things